Vectors also have a sort of arc length. For two dimension, it's the integral of the square root of dx by dt squared plus dy over dt squared. We can make this three-dimensional. Zoom out a little bit and just add the z component. Of course, you have to have integrate over dt. It's also more compactly just this a to b, the magnitude of r prime of t vector dt. For example, if we have r of t equal to 8t 3 sine of 3t and 3 cosine of 3t, and we want to find the arc length from this if the curve is from 0 to 2. We just set up the integral from 0 to 2 and we have our square root, and we take the derivative of r of t component by component, and this is 8 squared plus 9 cosine of 3t and square that plus, and that's minus 9 sine of 3t squared, and then we're integrating that with respect to t. So next we're going to simplify what's inside the square root. So 64 plus, that's going to be 9 squared cosine squared, so 81 cosine squared 3t plus 81 sine squared of 3t, and because those sine squared plus cosine squared is equal to 1, it's just the square root of 64 plus 81. And we're integrating with respect to t, but this is a constant, so we could just pull that out. So we're just left with, and that's going to be 145 times t evaluated from 0 to 2, and that's just 2 square root 145. And that's how long the arc length is of this function. It could be, it's going to be some curve in 3 dimensions. It could be like something like that, and we want to know how long is that curve, and it's this long. Of course, that's not the actual shape of r of t, but that's the point that I'm trying to get across, is that it's going to be some sort of shape, and it's going to be this long, but it could be winding and curving, and the entire arc length, the entire length of this thing is going to be 2 root 145. Anyway, thanks for watching.